Ruckus is a company that prides itself on its RF, or radio frequency performance. Now, along with some of the fancy antenna stuff you've heard about or going to hear about Ruckus, there are a few other things that we need to go over. For example, RF channels. What channels are actually available and what can be used in different regulatory domains? 2.4 versus 5 gigahertz, DFS, automatic AP channel assignment and adjustment, and automatic power adjustment. So this is a bit of a glance at the channels available in both 2.4 and 5 gigahertz spectrums. Now, it shows intended use, non-overlapping channels, number of 20 megahertz channels. So let's take 2.4 for example, probably the most popular out there. There are 3 non-overlapping channels, 1, 6, and 11 in North America, 1, 7, and 13 for some of those countries that have the upper band, or the upper part available. Number of 20 megahertz wide channels. So there's 3 channels available, these 1, 6, 11 for example, in 2.4. But if you were to channel bond like you can do in 802.11n, you only get 1 channel. Now, a quick piece of advice probably before it's ready is don't ever do that. Don't ever channel bond in 2.4 because you go from 3 20 megahertz channels to 1 40 megahertz channel, and the net result is you don't have as much throughput. DFS, dynamic frequency selection, tells you if it's required or not. Here's the different channel numbers that exist across each particular channel set. ISM, Industrial, Scientific, and Medical. UNI, Unlicensed National Information Infrastructure, 1, 2, 2 extended, and UNI 3. And to be really technical about it, in some countries there actually is an ISM channel above this, channel number 165. In the beginning of Wi-Fi, 2.4 gigahertz was, and still is today, by far the most popular. It's very inexpensive, the chipsets are really cheap. So what happened is a prolific number of 2.4 gigahertz devices exist, not only in Wi-Fi, but in other devices as well. Well, the reality is that 5 gigahertz has always been far superior. 802.11a was released in 1999. That first introduced us to 5 gigahertz, but it was too expensive, it didn't have as good of a range, so people didn't really adopt it. Today, when you're designing a Wi-Fi network, 5 gigahertz is very, very important. You gain so much. If you just look at that last slide, look at how many channels we have. 3 here versus 23 channels there. Channels equals throughput. So 2.4 versus 5 gigahertz always wins. What about range, you ask? Well, in any type of high density network, range is something you want, but the difference between 2.4 and 5 gigahertz in real life range is actually very slim, especially since there's so much more noise on 2.4. So remember, everything is about signal to noise ratio. 5 gigahertz has more channels and less noise, at least less noise for now. DFS. So the military and weather used to have, still uses radar on some 5 gigahertz spectrum, but the FCC, at least in North America, the FCC allowed us to start using that. The advantage is we get more channels, and that's what we're always after, is more spectrum to actually use for Wi-Fi. So the problem is that Wi-Fi was said that it could interfere with this military radar and weather radar. So to do that, you have a system called dynamic frequency selection that checks for radar signals. Then if it doesn't find anything, it'll select that channel. It continuously monitors for any radar on that channel. If it's detected, it's going to vacate the channel. Now, the other thing it does during that time is the access point sends out a message saying change channel. It's actually called a CSA, a channel switch announcement. Hey, everybody, change channels. The big problem with this is it's a bit like talking on a CB radio. It's like, hey, we're on channel 10, go ahead and go to channel 7. If you don't wait for everyone to acknowledge that they heard that part, that they heard that message, some people will be left on the old channel, and that's what can happen. Once an AP sends out a channel switch announcement, there's no mechanism to say that every device heard it. So what you can do is you can actually orphan some of your clients, and they're going to have to reassociate. From their perspective, the AP just left. So you never want to change channels unless you have to. It's really last resort. But DFS, the regulations make us do that. So it is a consideration when you're deploying Wi-Fi that you should very much consider not deploying on those DFS channels, those UNI2 and UNI2 extended channels. A good site survey with good background data put in place can tell you whether you should use those channels. What I do is I put a system in place, the system you're going to implement, in this case Ruckus, put it in place with some 5 gigahertz systems on those channels and watch to see if it detects any radar. You actually see it as an event in the event log. And once they do switch off that, it's going to have to stay off that channel for up to 30 minutes. But in real life, you don't want your systems changing channels on you unless it is absolutely necessary. It just has too much of a dramatic negative effect on the performance of Wi-Fi. One of the great things you'll hear over and over again about Ruckus technology is what we call adaptive antennas, also known as beamflex. It's a smart antenna system, of which this is an example. There's multiple versions of it, depending on the product. The idea is, in one slide, is to say it directs signal. It's like a dynamic directional antenna. If you take an omnidirectional antenna, which is kind of like a light bulb or a candle just out there, it has all the signal going everywhere. What this does is it dynamically focuses that signal directly to a client. What you end up with is more signal to the client while actually creating less noise. So Wi-Fi can be its own biggest source of noise. But before I go down that path, which is a very long soapbox session for me, just understand that when you can control the direction and intensity of radio frequency, you really have something there, especially when dealing with 802.11n. 11n has got things called spatial multiplexing, channel bonding, maximal ratio combining, and all these neat technologies that can even further take advantage of an antenna system like this. Now, if an AP has to change channels, which in some cases it do, our system can do that. If you have an access point on channel 1 and some major source of interference comes onto channel 1, we will automatically change channels. Now, this is very much like every other vendor out there. They have some sort of system that does this. The big differentiator is when we have to do it. Since we can give more signal to our clients, and what the real important thing is something called signal-to-noise ratio. If that phone is generating noise, then we just need enough signal to overcome that noise. And so when you get more signal, i.e. with beamflex, that extra signal can actually prevent a channel change from occurring. Whereas other vendors with omnidirectional antennas may have to change channels to overcome that noise. In a lot of cases, we don't have to. But there are cases where you do need to change channels with a high source of RF interference. In this case, our system does that automatically with no user intervention. Our system can also adjust for power. So if you're in a situation where you have multiple access points, that can cause what's called co-channel interference. Sometimes you need to reduce your transmit power. Again, in vendor comparison, us versus them, when we transmit more signal one direction, the other significant advantage is we're not transmitting it towards another access point. We're actually reducing co-channel interference. So if you only have 3 channels to deal with and you have 6 access points, you have APs that are duplicating channel. So the goal of any good Wi-Fi design and good Wi-Fi system is to minimize when those two APs on the same channel can hear each other. You can minimize that by reducing transmit power and or by directing the signal only to the client. So that's a very important piece. Now, if our system is deployed in a very dense environment, meaning a lot of access points with say drywall construction where the signal penetrates the walls very easily, then our system will automatically reduce the power. But we typically don't want to sell a system where you're going to have to put in more APs that will make it reduce power. With the antenna technology combined with smart channel design, you'll find that our system will rarely have to adjust transmit power. Another advantage to adjusting transmit power is if your system did adjust the power down, then if there's a fallen access point, you can actually accommodate for that. So if an AP fails, then you can adjust for that. You can actually increase the power to accommodate for that fallen AP. But as I've said before, a Ruckus system very rarely will reduce the transmit power unless the APs were just deployed too densely or in kind of an odd environment anyway. Well, I'm hoping this gives you a good idea of all of the things that a Ruckus system can do to work with radio frequency. Again, RF is one of those things that Ruckus is very, very good at, known to be the best in the industry because of all the things you've seen in that segment.